Okay, so we are in section 13.4. We're going to be working still with vectors, and we're learning a new operation today called the dot product. A dot product, we use the word product because it is like a multiplication between two vectors. And we are going to learn two different types of multiplication between two vectors. The second method of multiplication is called a cross product. And we're going to learn that. That's going to be the very last thing that we do this year. We're going to go over some matrices first. But now we're going to first learn dot product. It's the simpler product. One important thing to note is that the answer when you multiply these two vectors is not another vector. So what could the result be? What is it? The result is actually a scalar or just a number. Just a plain old number. That's what a dot product evaluates. It's just a number. So we have two methods for computing dot product. There are two definitions for how to compute a dot product between two vectors. One is through components. And so I have written here U and V, and I've given you their components. And the dot product between them, if you know their components, it's just the products of the first. And then you add to that the products of the second ones. Okay? And then whatever that answer is the dot product. Also, there's a second way of computing dot product, and that's if you know the magnitudes of the two products and you know the angle between the two vectors. So here the dot product is the magnitude of one vector times the magnitude of the other times the cosine of the angle between them. Okay, and so here we have some examples in which we're going to compute dot products. In 1 and 2, I have given you components. And so for u dot v on number 1, I'm going to take the two x components, 2 and 5, and I'm going to multiply those together. Then I'm going to take the two y components, negative 1 and 2, and multiply those together. So we get 10 minus 2, or 8. So the dot product is 8. On number 2, you also have components. You just don't, they're given to you as the coefficients of these unit vectors. So u is negative 2, 4, and v is 4, 0. And so the dot product u dot v is just the product of the x's plus the product of the y's. And so that's negative 8. All right, and then in this last one, I'm going to use the second definition of dot product, in which the dot product between the two vectors u and v is the magnitude of u times the magnitude of v times the cosine of the angle between them, pi thirds. And so to do that, I just need to fill in. That it's told the product or the magnitude of u is 4, the magnitude of v is 9, and then I need to do the cosine of pi thirds, that's 1/2. And so this answer is 18. All right. I would like for you to write down the 5 properties of dot product. It is theorem 13.6 on page 836 in the book. So go ahead and pause the video and do that now, and then come back. All right, and so since we have two ways of computing dot products, then one of the strategies that we're going to use to determine an angle between two vectors is to compute the dot product two different ways and solve. And so here I have component form, and so I can find the dot product between u and v very simply. The product of the x components plus the product of the y components. And so that gives me 36. Okay, so I know the dot product is 36. I also know that the dot product should be the magnitude of u times the magnitude of v times the cosine of the angle between them. And this is what we're looking for. That's the question. Find the angle between the vectors. Find theta. And so I am looking for cosine of theta, but I know the dot product is 36. So I can fill 36 in for u dot v. Also, if you work on this, the component or the magnitude of u is square root of 45. The magnitude of v is square root of 80. And so now my only unknown is theta. I can find the, and I know, and so this gives me 36 equals 60 times the cosine of theta. And so I know that the cosine of theta should be 3/5. And I would have to do the inverse cosine of 3/5, and that would be 0.927 radians, or 53.13 degrees. Okay, you just have to do the radians. I'll give you nice ratios that you know, so that you don't need a calculator. I obviously used a calculator to compute theta there. All right, and so now we're going to get into some new language, some big kid language about vectors and I guess properties of them, or interesting features of them. One of the new things we're going to talk about is this word orthogonal. Orthogonal is somewhat fancy, but it really just means perpendicular in this case. It means that the angle between the two vectors is 90 degrees. Okay, so let's suppose that that's our theta, that theta is 90 degrees. What happens with the dot product if theta is 90 degrees? If your two vectors, u and v, are at right angles, then what is the dot product of u and v? Well, it's going to have to be 0. And why is that true? That's because of the one definition of dot product, in which you use magnitude u, magnitude v, cosine of theta. And there it is. What's the cosine of 90? It's always 0. And so if the dot product of two vectors is 0, then we say the vectors are orthogonal. So here I have an example in which I want to know the nature of these vectors. Are the vectors at right angles? Maybe they're parallel, or maybe they're neither. And so to answer that question, I'm just going to find the dot product. What is u dot v? So the product of the x components is -8. The product of the y components is 0. And so my dot product is -8. This is not 0, so I am not orthogonal. Okay, how would I know if these vectors were parallel? Well, to know if the vectors are parallel, they would have to have the same slopes. And slope is change in y over change in x. And change in y over change in x is it's just y component over x component. And so you can look, this is completely horizontal. This would be 0 over 4, or 0. This has a 0 slope. And this one has a slope of -2. And so we're not parallel either, because the vectors are not pointing in the same or opposite directions. And so this is a big fat neither. All right, last topic is again a little bit trickier. We're going to talk about vector projection. This is definitely something that you use in physics, although maybe not so mathematically worded. But what a vector projection is, and this is my language here, it's not completely accurate to say this, but it's the right idea. It's the amount that one vector is in the direction of another. It's like the component of one vector in the direction of the entire other vector. And what we have in this box here is the definition of how you find that projection. Okay, and so this is going to be our final example. I have the same two vectors u and v here, and we're going to find the projection of u onto v. And I'm just going to follow this definition in this box here. So the projection of u onto v is, I need to find the dot product between these two vectors. I actually just did that. That was -8. Then I needed to divide that by the magnitude of v squared. And so the magnitude of v is just 4. That's a simple one. So I'm going to divide by 4 squared. And then you multiply this by the vector v. Let's put this in component form. So 4, 0. And so the projection of u onto v is simply -1/2 4, 0, or -2, 0. And then there's one more part of this question. I am asking you to write the original vector u which incidentally, the only time that was used was in the dot product, is to write u, which is negative 2, 4, as a sum of two vectors, one of which is this projection of v onto u. And so what is this second vector? Let me kind of draw you a picture of what's happening here, and we'll see it's very simple to find that other vector. But negative 2, 4 goes left 2 and down 4. So this is my u. This is u here. And v is the vector who is just simply 4 to the right. 4 to the right. So here's v. Okay, and did we get a negative? Yeah, we did. Okay, so if I take u, and I'm going to kind of put him at the end here, and that's because we got that negative. But if I take u, and I write u as a product of those two, or as a sum of those two green vectors, one of them has been v. It is v, and that's because we have that negative 2. Anyhow, so what must the other vector be? So this was the projection vector of u onto v, and so what must this other vector w be? I'm going to just call it w. Well, projection of u onto v plus w should be that blue original u vector. And you just solve this by setting these vectors equal to each other. So the projection vector was negative 2, 0, right? And w I'm looking for, and that has to equal my original u vector, which is negative 2, 4. And so I just need to subtract. So w is 0, 4 when you subtract the negative 2, 0 over. And so my final answer is that u equals the projection of u onto v plus w, which is negative 2, 0, plus 0, 4. And I know we had some zeros, and it's really easy to see that in this case because u was just negative 2, 4. But we won't always have zeros as the one component. Okay, and we are finished.